Hi, this video is a quick introduction to the DFN Generator. This is a tool that's been developed by Michael Welch and Mikhail Lucci over the last few years at DTU to simulate the growth of natural fractures and produce digital representations of fractured rock, for the purpose of modelling the processes that occur in and around those fractures in the subsurface. So for example, fluid flowing through some kind of reservoir, or the containment of different contaminants of concern, and this kind of thing. So within this video, I'm not going to try and give you the full background of everything, but I'm going to just try and show you a couple of the images that sum up the kind of outputs that you can get out. So on the right hand side of this slide that we're looking at, you can see 3 DFNs that have been produced using the tool in black, green and yellow. And then we can also see a layer of the predicted strain for this area over a salt diaper in this case. If we look closely at the fractures themselves, the interesting thing that you can already see is that we see a primary trend of fractures with minor trends of fractures cross-cutting between them. We can see that we have some isolated tips, some tips that are probably terminating in relays, and also truncated tips, that is fractures that have grown to the point that they have ran into another fracture and so can't propagate any further. If we look at the orientation of these fractures, we can see that orientation is changing around the peak of the diaper or the antiform in this case. And that's being controlled by the distribution, or rather by the predicted distribution of strain around the area. So, as I say, the purpose of this video is to kind of inspire you to go and visit the 2 resources highlighted on the right hand side here. One is our book on the whole process and how this method works, and secondly is to potentially even download the DFN Generator code, which is available as C# source code and also an executable that you can download and run as a standalone piece of software by itself. If you're a user of Schlumberger's Petrel software, there's also a pip file which will now enable you to install it directly as a plugin to Petrel. And at the end of this video, I'll actually switch over to Petrel and show you this slightly more human-friendly interface as well, so that we can work through a quick example and show you what it looks like in 3D. So, to come back to the problem that we're trying to address, on the left-hand side of this slide, we can see that we have a orthorectified image of an outcrop of fractured rock. We then have an interpretation of that rock, where in red we have the larger faults that have been observed, and then we have black lines indicating where we are observing fractures within the model, or rather within the outcrop. Over on the right-hand side over here, we can then actually see that we've inserted the red lines, the faults, as controls, and then we've simulated the strain distribution and fracture growth around those. And we believe that this provides a reasonable comparison or reasonable representation of the fractures in a digital form. So these fractures could then be exported as polylines or as 3-dimensional features and used for other forms of modelling in terms of whatever you're interested in. That could be fluid flow, it could be heat flow, it could be chemical spreading, whatever you fancy. And then on the right hand side we have those 2 images that I showed you on the last slide already. So in very brief form, how does this work? So the clever thing behind this code is something that Mike Welch realized some time ago, in that typically we represent fracture networks as a population length distribution diagram that looks somewhat like this cumulative frequency diagram that we have in the top left here. For fractures that are layer bound or smaller than a layer, there are rates. There are calculations that can be used to calculate the expected growth rate for those fractures. Therefore, if we know the distribution of sizes, we can try and back calculate the distribution of their nucleation times. So in essence, what this approach does is it back calculates the temporal distribution of nucleation of fractures in time, and then it seeds fractures related to the spatial distribution of strain rates at those times, and it allows the fractures to grow such that they continue to grow until they start interacting with either the bounds of the layer that they're within or with other fractures that they can be running into. And this is imaged, or rather this is illustrated on the right hand side of this slide, where we have little orange circles representing microfractures. That is fractures that are that have a diameter that is less than the height of the layer within which they exist, and they're growing. And then as we move to the right hand side of this image, this is time progressing, and we can see these orange microfractures are growing and growing. Some of them grow to such a point that their diameter is equal to the layer, and so they're converted into macrofractures that are represented as these blue squares. That also represents a change in the equation that guides us in terms of how fast they're going to be growing, and they can then be simulated as having growth extending out to the sides. All throughout this process, if fractures either end up within the stress shadow of one another, they could be implied to be likely to form a relay, or they can truncate into one another, or they can simply form an isolated fault tip within the model. So we have three different types of connections for the tips of those fractures. And as you can see, as we progress from the earlier stages of the model to the later stages of the model from left to right, we get an increase in the connectivity and also an increase in the density or intensity of fracturing within a unit part of the rock. This in itself is representative of one of the key advantages of this type of modelling, in that we're trying to model the way in which fractures grow and interact with one another, and so you get geometric rules that are followed. And within the book we've shown some examples of how we think this is representative of what's seen in natural outcrops. So, looking at a subsurface example, in this case from the northeast Netherlands, we've produced discrete fracture networks for three different formations within this area, all overlaying that salt diaper, or this antiform that we mentioned earlier. The exact details of the geological setting aren't too important for what we're doing. What we can see here, though, is on the left-hand side of this figure, we have implicit maps, so they're gridded maps in which each cell is populated with a number that represents the intensity of fracturing within that location. And we can see that in different formations we're producing different maps of fracture intensity. On the right hand side, those implicit calculations have been used to calculate a discrete representation, the discrete fracture network, and we can see the individual fractures growing into one another as we go along. If we take this green example, the Lower Holland Formation, we're going to take these images, in this case labelled as G and H, and look at a zoom in of them directly from above. The thing that we want to highlight here is that we can see that we have varying orientation of fractures as we move around an area, and we also have a varying balance of the relative number of major trend fractures and minor trend fractures, that's or primary or secondary fractures, as you move around the area. Also, if we compare the example from G and the example from H, we can see within the area of H, which is on the flanks of a salt diaper, we have a much more uniform distribution of the orientation of the major fracturing trend, and we also have a much greater anisotropy in terms of the fracture. That is to say that the major trend or the primary trend is much more dominant than the secondary trend. Whereas on G, Overall, we actually have a slightly more isotropic system, where across the entire sample that we're looking at here, we have a greater spread of orientations of fractures as we go around. As I say, we've actually grown or simulated the growth of these fractures within the model. So on the left-hand side here, we're showing a depth map to the top of the formation that we're modelling, with the salt diaper in the middle, so we can see the red showing shallower depth. So this is the top of that dome or the antiform that we were looking at. On the right-hand side here, we now look at a different type of representation of those fracture networks. Within this model, we can see that there are different colours as we go around, and if we look at the scale bar, we can see that these fractures are actually coloured by their time of termination. So this is the timing at which those fractures stopped moving. Now, a couple of interesting observations here. One, although this is a single model run, we've actually divided it into time slices so that we can see how a fracture network is developing over time. So as you might expect, the strain rate estimates are greatest towards the center. So with the earliest nucleation of fractures is towards the center, and overall the trend is that the fracture network grows outwards with time as we go along. However, what you may have also started spotting is that the latest stage of fracturing is purple. And if we look closely, we can see that there are actually quite a few purple fractures spread within the middle here. And then if we start looking more closely, we can see there are even some green fractures and perhaps even a couple of oranges in here. Now, the thing that is representing is that as the fracture network evolves, it's not only growing outwards, but we also have infilling of the existing fracture network. So what this is suggesting is that at 32,000 years within the model run, there was still some space within these fracture networks where the strain had not been fully accommodated. And so with time, that was then backfilling it in. Interestingly, we can also see that those backfilling fractures are probably a bit shorter and a little less dominant than the early fractures that were already there, which is consistent with the idea that we have fractures filling in what little space is left between the pre-existing fractures later on. So, what's this all about? I think that what you can probably see from that is that these models of fracture evolution are geologically guided by our estimate of how strain is varying around the area in terms of both the relative intensity of fracturing in different orientations and the orientation itself. The fracture size distribution that is normally used to prove or to validate fracture interpretations do fit, and in our case are guided by geomechanical principles. Interestingly, and probably the key thing that makes this method stand out against other DFNs, is that fracture connections are honoured and they're represented in a way where you could actually look at outcrops and start to try and prove what is the relative ratio of isolated tips to truncated tips to relay tips. This is an extra layer of interpretation and an extra way in which we can validate the models afterwards. If we're thinking of fluid flow or even strength applications, this connectivity of the fracture network could also be critical in terms of what the impact really is for fluid flow or contaminant spreading throughout an area. The other thing to notice is, as you saw with the diagram on the last slide with different time steps, it's very easy in this model to produce multiple realizations or multiple versions of a model. We could easily vary the strain that we think is occurring in an area and create multiple models, or we could take different time steps and take them as different likelihoods of fracturing. We could say that the areas that, for example, fracture earliest are perhaps the areas that are most likely to be fractured, while the later fracturing areas might be less likely to fracture. There are different ways that we can interpret this information, and that all enables us to apply stochastic methods in application to whatever our actual area of interest is, whether that's fluid flow modelling or thermal modelling or chemical spreading. That is open to you to use how you'd like. So in the remainder of this video, I'm going to switch over to using Schlumberger's Petrel software and have a quick look at what the tool actually looks like when we look at it in a plugin, look at the user interface that you can work with, and have a closer up look at the fractures and what they look like in 3 dimensions. An example of a DFN that's been produced by the DFN Generator, we're going to zoom into the Annelussat diaper located up here in the northeast of the Netherlands. If we take a look at the area, we can see that there is an antiform in the centre of this area that is the Annelussat diaper itself, and that actually sits within a salt mini basin with a couple of other salt walls around it. If we turn that layer of fractures back on, we can then zoom into this area and we can see the DFN that's been generated across that area in quite good detail. So here we can see that the different coloration of these fractures is actually a change in dip, and that's the light reflectance that's coming off of them. We can see that we've got orientation varying as we move around the structure, and if we look closely here we can see these kind of squares. These are actually the modelling rectangles, so they're the cubes within the geocellular model. So for each square within the geocellular model, the fractures are modelled, and then if they reach the boundary they'll then be continued through changing direction as they do to the local orientation. Things to note in this example are that this changing in colour, we can see that the fractures do truncate up against each other, and we can see that fractures in all orientations have varying dip as you move around the structure. So we do have actually a 3-dimensional fracture network. That is also represented as an implicit output. So as I mentioned earlier, an implicit output is where we have the small squares of the geocellular model itself. That's the background grid that we're modelling on, and each of those squares hosts a number that is representing some parameter of the model. So that may be fracture intensity, it could be fracture porosity, or a number of other parameters that we have listed here. And they're listed separately for different sets of mode 1 and mode 2 fractures. If we move on finally to the last example here, we can start taking a quick look at what different fractures look like. So if we move on to the next tab, we can take a quick look at an example of actually running the model. So probably the first thing to note here is that in order to run the model we need some kind of estimate of strain rate across the area. There are a variety of different ways of getting to strain rate. 2 methods that we typically use are either backstripping across an area or using curvature as a proxy. In this case we're using the curvature of an interpreted surface as a proxy over the area of the Annelussat diaper. So the minimum strain azimuth is taken to be equal to the azimuth of minimum curvature from the layer, and then we also use the magnitude of minimum and maximum and intermediate curvature to back calculate an appropriate relative value for minimum, intermediate and maximum strain. If we flick through these parameters, they're each saved as a grid within Petrel, and we can then have a look at actually applying that into the model. So once the DFN Generator plugin is installed, it's available down in Processes down here, and we can simply open it up, enter in our model name. We need to identify which grid we're actually working with, and we need to give the model an area to actually work with. So to do that, I'm just going to pick another view here, and if we use the select tool, click on a cell while we have a grid active, then down on the bottom right here we can see that there's a grid cell parameter, and that's giving us the coordinates in I and j of the cell that I've just clicked on there. So if I just pick this cell here, we can see down here we've got 181 by 135. So I'm going to just put that in as my start column and start row. They should be in order of I and then j. We then want the number of columns or the number of rows, that's the number of cells across that the model is going to be. So if we just simply make that 4 cells in each direction, I'm then also going to label which cells this should be looking at in the vertical sense. And in this case, I'm simply picking a depth that I happen to know works from previous models. Ideally here we'd be picking the k-index that correlates to a specific stratigraphic interval that we're interested in. So minimum horizontal strain azimuth, we're going to take the emin-asi here. As you can see, we do have default values in here. If we didn't insert grids into these sections, the default value will be used instead. And in fact, that's what I'm going to do here. I'm going to take the minimum horizontal strain azimuth as detailed by a grid. I'm going to put the minimum horizontal strain itself, that's emin-mag, in as a grid. And then I'm actually going to use the maximum horizontal strain rate as default 0, so that'll be uniform across the grid. Here we can select whether we want to generate an explicit DFN, so it's worth noting here that the tool has to always create implicit outputs, but actually the DFN is a secondary option, so it can be worth running without the DFN output first just to check that it completes, and then coming back, revisiting and running again. In addition to this, we can also output a number of intermediate outputs. So here I'll just put 2 intermediates, so that what we'll expect to have is 3 time steps with 2 sampled equally throughout the total duration of the model run. If we go through these, we can also look here and we can pick out the Young's modulus, for example. We could insert our own Poisson ratio, biocoefficient, or other mechanical properties. Or again, we can insert a default value that will be applied across all cells within the grid that we're looking at. A couple of particular parameters here to watch out for are the physical property of Young's modulus, and also the initial microfracture density and the subcritical fracture propagation index. If you check out our book, you'll see some nice sensitivity testing of this. Essentially, what you should expect is that the initial microfracture density is going to determine how many small fractures are initiated at the very beginning of the process in initialization of the model, and the subcritical fracture propagation index is going to strongly affect how quickly those fractures grow. So if we have low microfracture density and high propagation index, would expect a relatively few number of long fractures. On the other hand, if we have a very high number of initial microfracture densities and and a lower propagation index would expect many more shorter fractures that are all going to be interacting with each other. We can then come through, we can tell it what depth of the formation will be at the time of deformation. If we don't input anything there, then the model will simply take the depth of the model that we're working with in Patrol. We can also then input some simple parameters so that it can calculate what the stress conditions at the time of deformation would be. In terms of outputs, it's worth mentioning that we can write implicit fracture data to file, which will come out cell by cell across the whole grid, so that's a lot of data. Often we don't want that much data. And we can also output the explicit fracture data, so that's the DFN, and we can choose whether we want that as a normal ASCII file or as a Golder Associates fab type file. And you can see we have various other parameters here that will help us calculate, for example, distributions of fracture aperture according to Barton Bandis or fracture porosity across the area. And in the control parameters, we then have additional controls which generally we don't need to work with. So I'm going to hit apply on that quickly, and we're going to see this starting to generate the model. So you can see it's already done one implicit and it's now generating the explicit, and now it's moving on to rating the data as an ASCII format so that we can actually have a look at it afterwards. So we will just wait there for a moment, and I'm going to keep this going at a normal pace so that you can actually see how long the model takes to run. So there we have it, the model is run. If we come down to the bottom of the model window, what we'll see is that we have these two intermediate outputs and the final output as DFNs. There we have it. If we zoom in on that area, we can see that it started out in the red, the higher strain areas. If we turn on the next intermediate, it's grown away from there, and then if we turn on the final, we can then see that everything's now fully fracture saturated. If we actually turn those fractures on in the opposite order, we can then see the relative order and colouring. And I'll just turn the grid off in the background so that we can take a better look at that. So if we turn this off and the previous fracture pattern off, and perhaps if we just change the colour of the final output there to a colour that is slightly friendlier for us to see, there we have it. We can see that at the very end of the process we have the fractures in blue, the intermediate step is red, and the earlier in the process is shown in yellow. Within those fracture models, just like in the bigger output, you can see that we have varying fracture orientation, varying fracture dip, and we have that spreading and changing in intensity as you move across the area. So I hope that that's a useful introduction to show you roughly how you do a quick run and some of the special features of the DFN generator. And this video should be followed up with a couple of longer videos that give you a more in-depth discussion of how it works and why you might want to use it. Thanks.